Hello, Gabe. Hello, everyone. Welcome to the Versus AI webinar around AI benchmarks. And this is a special once every 4 years Leap Day presentation from Versus. I'm James Hendrickson. I am president of Versus Enterprise, and I'm joined by Gabriel René. Some forward-looking statements for you. These will be available in the deck as we make that available, and you know how this normally works. So here is the two of us that we're speaking. So Gabriel is our CEO and founder, and I'm president of the Versus Enterprise. And the way this session is going to be working today is I will ask some questions, sort of moderate this, go back and forth with Gabriel about what we're doing with the AI benchmarks, and hopefully give you an update on what's going on with that. So before we do that, let me ask the first question. Gabriel, do you want to say good morning, introduce yourself, and then we can get started on what on earth we're talking about today?
Yes, thank you, James. Good morning, everybody. Good afternoon for some of you, and perhaps good evening for others. I'm really excited to be here today to be able to share a bit of a nerdy deep dive into benchmarks and the underlying science related to the breakthroughs that the company has made recently, the implications for the industry, including, I think, our position in the industry, which is, I think we have very strong ambitions to become the market leader in this space over the next few quarters, and I guess how this all ties into our product timeline and our rollout plans, which we're excited to share with you as well.
Perfect. Thank you, Gabriel. So tell me a little bit, we're going to get started here with the first question, and it's an easy one. Tell me a little bit about Versus and what we're talking about from Versus approach to AI.
It's interesting because I've actually never had to read the sort of this statement in public before. Every Monday when the entire company gets together for our Monday morning meetings, which you lead, James, you review the company's mission statement and vision statement. We talk about it as a starting point, but I don't think we've ever really discussed it in this kind of a forum. So I don't want to just kind of burn through it. I actually want to take a second and kind of explain what some of these words mean to us, and in particular what they mean with respect to the industry and the market. So Versus is a cognitive computing company. First of all, we don't say we're an artificial intelligence company, right? Why? Because artificial intelligence to us largely means machine learning, and cognitive computing means applying the processes of cognition in the mind, which is the ability to update your understanding. Cognition is a process in computing. And so this is I think the important nuance that many of you may not get, but it is foundational to who we are as a company. And interestingly enough, one of the areas where we've always been focused is what we call spatial cognition. And so one of the assumptions that we work from is not that cognition is something that you can get from text, or that primary, or even concepts, but primarily that ideas are anchored to embodiment, and that's anchored to activities and objects and physics of the real world. And so spatial cognition has always been at the heart. The whole concept of the spatial web is quite central to what we do. The fact that we started working in warehouses and logistics and trying to get spatial understanding of how to route humans and robots faster in these environments was an indication of us starting not from just words to try to make sense of the world, but actually starting in the world. And cognitive computing is ultimately only going to be successful because it's successful in the world, not just in sort of abstract environments or in sort of cyberspace. So what we're doing, we're building next generation intelligent software systems. Again, we don't say artificial intelligence software. We're just saying it's intelligent software. We're not trying to make a mimicking sort of function for intelligence. We're trying to apply the actual processes of intelligence software. So as we understand it in the mind, and modeled after the wisdom and genius of nature. That phrase sounds a bit lofty to me. It's quite ambitious, but the two words there actually have two different meanings. So wisdom is, let's say, understanding the results of your actions, right? Wisdom is not just knowledge about the world; it's understanding what actually works. And when you look at multi-generational, or sort of like the wisdom of age, it's because you've had a lot of experience. You've been able to test your theories many times in the world. The kinds of agents that we make can actually learn from other agents. So it means you can actually transfer not just data or information, but knowledge and wisdom. So one agent learns how to do something in a particular environment, like an autonomous vehicle learns how to brake in a new way on some, dry ice in Detroit in a winter that the ice was a bit thicker than before, wasn't part of its training data like you would have in a deep learning model. It can learn how to brake by experimenting, some sort of hyper stutter step process, say with the ABS brakes, but then it can, using our HSML language and using the explicit sort of calculus that comes with active inference, can literally copy paste transfer that to any other agent powering any other vehicle in the city or in the world, right? That's the ability to pass along wisdom. And then there's the genius of nature. What do we mean by the genius of nature? So obviously our product brand that we're rolling out now is called Genius, but it is a nod to not just smart systems. We've been talking about for the last 15 years making things smart. We want things to be smarter. What do we think makes things smarter? Nature. Nature is the ultimate laboratory. It's the ultimate test environment. It's the ultimate, it's the ultimate classroom. And we want to be able to have systems that can essentially be more than smart. They can become increasingly smarter. And in whatever environments that they apply to, they effectively are applying that intelligence of nature, that genius of nature. So we represent a paradigm shift in the current approach to AGI, which is the idea that you can have human or beyond human level performance in software. And the paradigm shift is that we're basically deriving this from neuroscience as opposed to computer science. So we're more interested in applying what we understand about how intelligence works in nature to software systems, rather than just trying to reverse engineer intelligence or reverse engineer a brain in a computer. And it is the superpower that our company has, because we have done this zagging when everyone else was zigging. And I think that's a great place to start.
No, that's great. That's super helpful. Thank you for taking the time on that. And so you see this leaf in the background here, and that sort of represents this difference between nature and the alternative, which is an artificial approach. So my next question is sort of what does that wisdom and genius of nature mean, and how do the current people who are doing it today do this? There's a question that came in the chat I find fascinating, because it sort of is a representation of what we're talking about here. It's sort of, the question is, hey, isn't everybody else doing all of this stuff today? The ones that have invested in the current AI, aren't they doing what we're going to be doing? And so why don't you address what currently happens, Gabriel, and then maybe within that, we'll talk of the next part of it is what are we doing that's different, and weave in there what Meta and others are possibly doing today.
Yeah, great. So excellent question. It's one we get often. I want to just couch this by giving you some historical examples. So instead of me just giving you the direct answer, you can kind of contextualize this. If I showed up with a car called a Tesla, and it had a battery that powered the car instead of a combustion engine, and I showed you it driving around, and you'd say, well, what's the difference, right? How about the smartphone emerges, and I can make phone calls and I can text just like you can on my Nokia, right, or my BlackBerry. But what's the big difference, right? The big difference is in the entire design and architecture of that system. Does it do many of the other things? Yes. but it also does some things that other systems cannot do. And usually that leapfrog moment is when you get a massive paradigm shift in a product and engineering, and usually that is a result of some scientific breakthrough or some engineering breakthrough. So let me get more specific related to us. Artificial intelligence is a computer engineering process, right? It has to do with trying to make reverse engineer a brain in a computer. Now, for a second, I want you to think about how insane and absurd that sounds. We want to build a brain in a computer. Well, who's going to do that? Computer engineers, people with computer science degrees. What do they study? What do you study with a computer science degree? Computers. Do you study the brain? Maybe a little bit. Maybe some people do. There's some overlap here. But the real challenge is that the approach that they've taken is an engineering-based approach. It's actually an industrial process. More data, bigger models, more computational power. And they're hoping that this will magically lead to intelligence forming in that box. So it is literally an artificial approach to making intelligence, right? And so this is called deep learning. And until about 2012, when there was a breakthrough paper essentially AI algorithms that were trying to recognize images in photos, right? What was called ImageNet. There was a version called AlexNet, which was competing in this paper. This is going to get to the benchmark stuff we're going to talk about later. And Geoffrey Hinton and his team, who we now know as the godfather of modern AI, who had invented deep learning a decade earlier, but it hadn't really worked for about 10 years, and everyone thought it wasn't going to work, suddenly beat everyone else at this paper. That paper launches this 10-year run of what we all call AI, which has led to this multi-trillion-dollar industry. But the approach is more data, bigger models, more computational power. It's just trying to say, if I have many, many, many examples of the phrase, let's say in a text example, Jack and Jill went up the hill to fetch a pail of, if I've seen that a million times online, like ChatGPT has, and that's part of the data it was trained on, it's going to go with water. It's not going to go with jelly. It's not going to go with money, right? And so these systems are designed to pick the top answer out, essentially the most recurring pattern out of a data set. Now that works maybe 80-something% of the time. But what these systems do not do is they cannot adapt, they cannot incorporate new information. And if there's any scenario that they're in where they're training the environment or situation or context is different than what's in the training data, they just get it wrong. This is why yesterday we see Apple just saying we're shutting down our car business. Why? Because the software can't figure out how to adapt in situations where, again, it turns out driving is really dangerous. This is why autonomous cars have largely failed. Elon has come out every single year since 2013 saying it's coming next year. It's not coming. It's not coming next year because they're basing it on this artificial approach. Why? What's the big aha? These systems can memorize, select patterns out of that, memorize those patterns, and basically have a big bucket of knowledge, because they've literally just seen many, many examples and they're picking the top answer. What is that not? That's not cognition. Why? Cognition is a process of constantly updating what you know by figuring out what you don't know. And these systems only have 100% of the knowledge that they have. And they have 100% certainty about the knowledge they have. This is why ChatGPT and all these systems hallucinate and lie. This is why autonomous vehicles emphatically make the wrong decision. I was just watching a Tesla try to last week full self-driving. The woman was testing it and it just decided it's going to go in the other lane and just go around some cars, even though clearly the right thing to do was stop. So they don't fully understand. They just understand the top answer, where they call this the lottery ticket hypothesis. And so this is great for things that you don't need a lot of accuracy for. You want to generate a poem where you say, I want you to make a Valentine's Day poem for my wife, Teresa, in the voice of a pirate. It can do that because there's no real right or wrong way to do that. It doesn't need to be hyper accurate. You don't need to be right. It doesn't need to be very recent. It doesn't need to understand the multidimensionality of the environment. So and it doesn't need to, and most importantly, learn and adapt. So these systems are just giant industrial systems that are trying to extract the top answer out of a bunch of data. And that's the state of the art today. And it's useful for things that wherever that training data got the right answer and it applies in any of those situations, provided nothing has changed, you can get some pretty good results. Turns out the number one thing that happens in the world is change. And so the way intelligence actually works is it adapts constantly to new information. So maybe that's the way to juxtapose what we're doing.
Yeah. So just a couple points here, Gabriel. The first is we're not diminishing necessarily the massive advances that have happened in the artificial space. It's still incredible. It's just not enough. Is that right? You're saying?
I'm saying it doesn't work in many of the scenarios that it's designed to work in sufficiently for it to be safe and useful and functional.
But it's really
we've all been watching. James, we've been watching Boston Dynamics robot dogs, dance for 10 years, but you can't wash a dish. So I just don't know how useful it is, even though it's compelling. I think the research is interesting, but really, where are the applications? We haven't seen them. Even in the last year, you've got OpenAI coming out saying, 90% of Fortune 500s are testing, are using our technology. Well, who's shipped the product? Can you name one?
Nope.
So they're making $2 billion because everyone's testing. Everyone should be testing. These are useful technologies to experiment with. Are they fit for purpose is the only question in any market. And so I think that they're good at some things. Generating content, they're quite interesting at. I think they're great. They're amazing they're amazing brainstorming tools. I think it's the most exciting engineering I've ever seen. I think it's based on bad science. I genuinely do. And every shortcoming they have can be explained by that. Can literally be explained by that. It's right. So just because you cast, you can't see the image here necessarily, but they're, casting, green seeds, fresh data onto concrete is not going to grow you a plant. Right. And you can't squeeze enough apples and get an apple out of it. You can get apple juice, but you're not going to get an orchard. Right. And so there's just some fundamentals here that are just wrong. And I'll tell you one last thing, even though this is a bit nerdy out. It's because Jeffrey Hinton and others were looking at the research because they did base a lot of this on neural nets, which came out of, obviously trying to mimic aspects of the brain. This was based on what was called the computational theory of mind from last century. And that theory of mind said that humans are just input-output devices. You have your senses take an input, you run through a process, you give an output. What Carl Friston and others started to realize was that was actually not how the brain worked. And there was a huge thing around what was called enactivism, the idea that the brain's a prediction machine. You're actually pushing your guesses out into the world and then seeing whether or not your guesses are right. It inverts the whole process. Yep. And that whole modern paradigm, which has come out in neuroscience, these guys were still operating on last generation's model. And this is like having a BlackBerry or a smartphone or whatever. Yes, can you add the internet to a Motorola flip phone in 2006? Yes, and we all have these little horrible WAP pages with black and white screens. Apple comes along and says, flip the paradigm. You make one giant screen, you make a computer really small, you add the phone as an app, right? Tesla comes along and says, there is no gasoline, there is no big data. You don't have a combustion engine. You throw the engine out of the car, right? You build the whole thing around a battery. This paradigm shift allows for a transition. It's not to say mobile phones weren't amazing. They took it off the wall and put it in our pocket. But having 5 million applications and being connected to the internet was more important. And so ultimately, that's what we're talking about when we talk about this shift here. Artificial intelligence has led the way, and the breakthroughs that we see now are very significant. I mean, go back to the early days of the web. Large systems are great ways to start. AOL, Prodigy, like big portals. But what ends up happening is that a distributed model that flips that whole paradigm usually emerges. And then those other systems are toast. Like Nokia sold 1 billion phones in 2006, and then they died 3 years later. Like BlackBerry, Motorola. So these paradigm shifts happen, and the Goliath falls. It is the most common story in the history of technological innovation. And this is where a lot of our confidence comes from, because the underlying science, which we're going to walk you guys through in more detail today, gives us that confidence because we can prove it.
So let's talk about some of the natural pieces of it. So the flip side of that, I know you touched on it already a little bit, but talk about how the VERS approach is different, and maybe weaving in some of that, the newer models of the mind into our approach.
Well, so what I like to think of as cognitive computing, which is a subcategory of natural computing, which you're welcome to go on Wikipedia and look up natural computing. You'll see cognitive computing, artificial intelligence. Artificial intelligence is in that category. It's how do you sort of mimic how nature does it, right? And like if you look at this, it's not about reverse engineering. It's about applied science. What is it? What is a first principles approach? What is science? Science is say, how does this occur in nature? This is not an engineering problem. How does it occur in nature? Understanding it, then applying it. That's the difference between applied science. Reverse engineer is experimentation until you get it right. That's a process in science, of course, experimentation. But what you're trying to do is, if you can understand how nature does it, you don't need to do all those experiments, right? Your business is not a business of experiments, which is what the AI industry has largely been. So we're doing applied neuroscience, and it's about taking a natural approach to intelligence that grows, meaning that things can get smarter and smarter over time. You know, I all hope we're a little bit smarter than we were last year, probably a little bit smarter than we were yesterday. It's because all cognitive processes are learning and adapting in real time. Because the world changes and you change. If you're not able to adapt to the situations and environments that you're in, even think at great scale like evolution, you can't survive. So it's actually more important to learn what to do next than to remember what you did before. That's a great foundation to have a history of knowledge, but it often doesn't apply. And actual intelligence learns how to adapt to new information and incorporate it. So what we're talking about is not a giant computer, scale the machine. We're talking about growing an ecosystem, less data, small models that are able to tune themselves, that are autonomous. They use less power. And then what you get is something much more like the web. Many, many different types of agents that act like little Legos that can be assembled together, that can connect together. And so the realization is the same, right? Knowledge, which I would call artificial intelligence, is sort of compressed knowledge systems, right? Indoctrination as a service. They've got a compressed memory and they've picked out mostly some really good answers from the past. And often those apply to the present, but too often they do not. In this case, it's the same as knowledge is not cognition. You need cognitive computing systems, or you cannot apply all of this amazing knowledge to the dynamic, ever-changing, very complex reality of the physical world that we want to use these systems to automate. If they can't understand what they're doing, we can't automate them. If automation requires things working together or chained together and doing the relay race of the supply chain, anywhere where one of them doesn't understand, the chain breaks. So they have to learn in real time. They have to be able to adapt. And you can do that with less data, with smaller models and less power, which means you get something that's, better, cheaper, faster. And in any industry, better, cheaper, faster is the thing that often wins.
For sure.
So that's the difference.
Totally makes sense. So so Gabriel, I'm gonna ask myself this question, which is a moderator no, I think. But I needed to understand a little bit about sort of what the type of scale between these two things were, looking at it from a natural perspective versus an artificial perspective. So the way I thought to do this was, and again, just to clarify, this is we're not claiming this is our performance. I just wanted to get a sense of what the cost in energy and effort essentially was between one human thought and one query in ChatGPT, just to get a sense of this scale. And some facts about the brain. It's about a 20 watt, utilizing about 20 watts across the course of a day. Commonly believed that there's about 60,000 thoughts. I don't know if that number is right or wrong. I think many of us have more than that, but it's a starting point. So based on that, I did some math, and I'm not going to share the math with you, but I'm going to tell you about the math. So a human brain for one thought costs about 330 microwatts, and then ChatGPT costs about 1.7 million microwatts. Now, those numbers were so far apart that I actually had to play with I had to figure out what a microwatt was first to be able to figure out the difference between these two, and try to be able to make a point of reference. This is the only direct reference I could come up with, which this in the middle here is a red LED, which if you're not super geeky, the red LED is the least power consuming LED that exists. So I try to make this as small as possible, and we can power the human brain. 2 minutes is generous. Generally, I think we might be able to, that single thought might make that light blink. Thank you for moving that, whoever did that. For ChatGPT, that query will power that red LED for 42 and a half hours. So almost 2 full days will be powered by the single thought or single query. So again, we're not comparing these two and saying, hey, Versus is going to be as efficient as that. But that's the difference between the efficiency of nature and the approach of simulating nature and attempting to mimic nature in an artificial way. So there's my query. Anything you want to add to that, Gabriel?
I think this is what I would say indicative of the difference between how nature does it and how the current state of the art does it. But the main theme here is that you learn and adapt to new information in real time. You don't try to hold all the information about everything, and any individual human's not trying to hold all the corpus of humanity.
Right.
No single computer is even trying to hold all the data on the web. What you have is a bunch of different servers and different computers that can access that data. So you can access the web from a single computer without having to host and run and compute the entire web. So a monolithic approach is just not an ideal approach. It's just going to cost you much more. And there are better ways to get fresh, updated data. So, ChatGPT is just a machine that is running a process that is fixed in time. It's Encyclopedia Britannica 2023. What you want is Wikipedia. You want Wikipedia. You want the dynamic range of lots of different updating pages and links that are constantly evolving and shifting with the real-time information of the world. That even self-heals when data is inaccurate, as opposed to ChatGPT. We cannot change the underlying data because it's frozen when they ship it. It's just a machine process. It's not cognition. It's not learning that after they ship it. And this entire learning process is mediated by thousands of humans telling it the right answer. It's not doing the thing that we want it to do. It does something that looks like the thing and works some of the time in some situations. Non-critical situations, it's I think decently useful for, but most of the real world automation when you ask about multi-trillion-dollar market opportunity, it just doesn't apply.
Right. So we're about 30 minutes in. We promised benchmarks. Let's start framing the benchmarks now that we've gone through some of the background of our approach and why we are doing what we're doing. So I think I'd like to know about what some of the advantages are and what around modeling it after nature. And then if you could set us up for the beginning of this conversation around benchmarks, I think that'd be great.
Well, one of my least favorite phrases in business happens also to be one of the most applicable here. What are we doing? It's just a better mousetrap. So I want to see why benchmarks matter here. So what is Versus doing differently? We have a better, cheaper, faster approach to intelligent software. So why is it better? It's smarter because it can learn in scenarios outside of the data it was trained on. It's safer because you can actually see what the agents think before they do it, and you can audit the decision-making process. It's more sustainable because it uses significantly less compute and less energy. It can operate at the edge. And really interestingly, you can have agents that can share information between each other and actually get smarter together, exchange skills and capabilities even. It's faster because it can operate on small devices at the edge. You don't need a massive compute architecture. You don't need NVIDIA GPU like clusters, right? Because a lot of this intelligence we want needs to be at the edge, on robots, on drones, on toys, in cars, those decisions need to be made right there. You don't have time to go to the cloud and ask, should I turn left? Should I brake? Should I stop? But so that means it has to be faster, not that just that we enable it to be faster. The market demands faster. And then cheaper. That's everyone's favorite word in business. The amount of data that it needs to train on is orders of magnitude less. And we're going to show you some examples of that. And most importantly, that you don't recognize, every time someone's got to make an encyclopedia over again, just like GPT-3 and GPT-4, you got to basically scrap, in the case of GPT-3, the entire thing. These things, it's called catastrophic learning. So I train one model, it learns. It doesn't get smarter. I can't make it smart. I have to scrap it. I can train it on the same data. I usually add new data, and I use that same algorithm, but I produce a new product. That's Encyclopedia Britannica 2024. That's a machine process. Something that learns and adapts in real time is something else entirely. And so this continuous learning means you do not have to you don't have to do retraining. ChatGPT, GPT stands for General Pre-Trained Transformer. Transformer is a type of deep learning model. Pre-trained. It's trained. It trains on that data. The next version is the next version. This is not about versions. This is about continuously learning adaptive agents. Better, cheaper, faster. This is what we're doing. And the benchmarks that we're going to show you demonstrate each of these capabilities. And that's why they're significant. It's the first real examples of the evidence that we can deliver on the promise of a better, cheaper, faster approach to intelligent software.
So before we get to that, one of the questions I saw in the chat as it's coming in, I think is appropriate here. This is sort of the reason why there's so much investment in hardware for AIs today. The opposite of what we're talking about is because we're throwing compute at the problem and hoping we get a better outcome. Is that right?
That's right. And we'll talk about that more, because when we talk about Atari benchmarks, that's exactly how they made it better. But that's not how biological intelligence works. And getting $7 trillion for global infrastructure for that is the exact wrong way to go. It's
right.
An absurdism. It's a nice way of failing up, but it's indicative of not understanding how the process works. It means that you've got a really good hack at it that kind of works, right? Like we did make flapping planes jump around a bit, mm-hmm. But you just can't fly from California to New York. You need to understand how aerodynamics works. So when you understand the science, the engineering gets easier,
right?
And you don't need power hacks, which is essentially what we're talking about.
Yeah. So let's start talking about benchmarks. What is as a starting point here? How do companies begin testing? Oops. On the wrong way. How do they begin testing AIs? What do they do? How do they test this initially?
Well, the whole point of AI is to make software do things that humans can do. That's largely what the point is. So games of strategy and games themselves have long been the benchmark tests because they're complex. And so chess was largely considered the domain of humans. And what's interesting, like ChatGPT is so incredibly interesting today because language is considered the domain of humans, right? And so we've seen this multiple times, and it is a powerful indication of the capabilities of these systems. It just doesn't mean they apply to all the real world automation that we actually need to benefit from. So you got Gary Kasparov, Deep Blue, and IBM, beat him in '96, and this was like a pretty big moment in the history of computing. Most of us were around, recognized like, okay, well, something's happening here. If you fast forward into the modern era where you have deep learning and reinforcement learning, Google then made something called AlphaGo, and in 2016 beat Lee Sedol at Go. I don't know the math. Maybe you do, James, but Go is a much more popular game in Asia, but it's like mathematically many times more complex than chess? Like the total number of moves is some, I don't know.
It's
like,
absurdly, it's close to double. So chess's total number of moves is 10 to the 123rd power, and Go is 10 to the 360th power. Which people who are better at math than me, it's probably not double, it's probably triple.
No, that's not.
And I think it's exponential.
Yeah, it's exponential. So every one, like what is it? 10 to. So every one after that was one more time. So you're talking about, I don't know. That's like number of atoms in the universe.
Yeah, really big.
So AlphaGo is also a proof of modern AI, right? And it's 2016, so it's not that long ago. And this is like the top algorithm in history, and sort of finally beat something that is so complex. So games that have long been the benchmark text, particularly initially like games of strategy and let's call it skill, the ability to sort of forecast into the future the moves that you want to do. But games ultimately are kind of fixed, right? There's not a whole lot of, other variables are not going to enter the game. In this case, you move some things around, some positions in space. Let's keep going because we'll probably get into
we start with these games, which are relatively we've beaten them. Humanity has beaten them from a computer perspective. What's next? Let's up the ante a little bit.
Well, computers have beaten humanity at those games. So then what started to emerge was, okay, what about games where there's lots of dynamics? So out of AlphaGo came AlphaZero, and AlphaZero basically learned to beat AlphaGo almost immediately. And so AlphaZero ended up being the state of the art. So then they said, okay, well, how do we take this up to the next level? And ironically, they took the Atari 2600 games from the 80s and said, this is in 2 dimensions, but it's actually quite complex. If we just gave the algorithm the ability to look at pixels and the score, could it learn that there are object permanence and things are moving, like through space and time, and that it needs to take certain actions in order to make the score go up? So from unstructured data, essentially, could you train algorithms that could learn to see and then act and then win? And this is actually, even though it may seem a bit trivial, that play video games. Well, when you show up to play a video game when you were 12, in 1987 or whatever, you come with a whole history and wisdom of embodied cognition, and you're able to apply that. You're talking about something that literally is like kind of just bursts onto the scene and has to be able to do that. So the Atari challenge then becomes a very significant challenge that is intended to indicate closer to real world scenarios where there are dynamics and objects and actions and change. And if you don't do something, you die. And so that's why the goal was, could we meet and exceed human performance, from near scratch.
So just to be clear, this is not the same as self-play mode where they pre-program the computer and we're doing a new computer versus an old computer. This is actually learning to play it as if you've never seen it before.
Correct. And if whoever magic person or AI moved our image, our photos before, if you could put us up in the upper right-hand corner, that's probably going to consistently be a good spot. Magic powers. So a decade in Atari, right? So where did it start? It started with what was called deep reinforcement learning, DQN. This is that Q learning that those of you that were looking at, last year, whether or not OpenAI had AGI, there was a lot of Q learning. Q learning's been around for a while. It's not AGI. Don't worry about it. This was like, okay, if you use 10 million frames, sort of give the AI 10 million snapshots of the game so it can learn about all the different states that things might be in. And then could it learn and play and get to human or above human level performance? And it did. And then they said, okay, well, so then mu0 is actually AlphaZero fine-tuned to be able to compete. So the most popular, most expensive algorithm in history coming out of Google. And in 2019, it beat everyone else with 200 million frames, right? And then one called Agent 57 did 100 billion frames. So I think in the end, that's like 11,000 years of human play. So we call this sample inflation. And again, it's kind of like ChatGPT. If you can just throw more examples at something, so you get more examples or more compute. And if you have both, you're going to pick out the top answer. in the system. That would just be table stakes for a computer. And that's what's happening here. So let's go to the next one. So then Atari 100K was proposed in 2019. What is 100K? It's 100,000 snapshots of the game. It's about 2 hours, not 11,000 years. Because the idea of this paper, and this is why these science and research and papers are foundational unlocks in artificial intelligence. Not every industry cares about underlying science or research. Biotech does, and AI does, right? So this paper came out and uses model-based reinforcement technique, and it said, asked this question: how can people learn so quickly? Not in years, but in hours. Part of the answer may be that people can learn how the game works and predict which actions will lead to desirable outcomes. And so in this proposed now a sample efficient approach. You're only given a few examples of 2 hours to basically try to play. And that then resulted in this new sort of test called the Atari 100K. Let's keep going.
All right. So let me see here. Do we want to talk about MNIST now, or do we want to go and cover this later?
No, let's come back to this.
Okay.
So
hold on.
Learning.
The reason we've taught you all of this stuff so far is because you need the context to know what we're doing. And we didn't want to teach you about video games or fancy sounding acronyms and things like that. The goal here is to get you to understand the benchmarks that everybody uses, right? This is not just something we invented. Go ahead, Gabe.
What's the next slide, James?
Yeah, do you want to dive into the breakthrough? Oh, sorry. There we go.
So you've got this Atari 100K setup. A few months ago, we came out and said, Versus has made a significant breakthrough. What was that breakthrough? In fact, go back one slide before. Is that the active inference? Okay, here's the premise, guys. There's a 15 trillion, 20 trillion, depending on which sort of research group you want to follow, AI industry that has just emerged here. 98% of that is based on the theory that deep learning is going to be the foundation for all that multi-trillion-dollar industry. And what we're telling you is we don't think that that's the case. We think active inference is going to be that. Why do we think that? It's because we've had a scientific breakthrough and we're able to do things these other systems cannot do. What is that breakthrough? So active inference, emerging out of neuroscience, uses a different type of mathematics than deep learning. Deep learning says, essentially, I'm going to take enough examples, millions or billions of examples, tons and tons of compute power, and then I'm going to give many examples to an algorithm who's essentially a randomization algorithm, and then it's supposed to try to pick out those top answers. Once it's picked out the top answer, we lock it in, and that top answer is all you have, right? And so this is why ChatGPT is so emphatically wrong. And then the system is so big, trillions of parameters, massive data center, that it's really difficult to go in and find anything or change anything. So go to the next slide. Mm-hmm. So the breakthrough was based on what's called Bayesian mathematics. Bayesian mathematics basically says that you can mathematically model the probabilities of whether or not certain informations or answer might apply. And this Bayesian approach in the AI space has largely been considered a more principled approach. It lets you model more details, more information, and then you don't have to have one right answer. There can be many different right answers, and depending on the situation, the right answer can emerge. This has largely been considered to be computationally intractable. So having this better sort of algorithm didn't scale to the types of applications that we've seen. We were able to have a breakthrough where we could show that you could scale Bayesian mathematics using active inference, where it would select the right data without computing on 99% of the rest of the data. And then we've selected Atari as a benchmark challenge to show that we can beat the state-of-the-art billion-dollar backed AI algorithms that are using deep learning that showcase greater efficiency, human-like learning and better performance. It's literally better, cheaper, faster in their own stadium at their own game. And so that breakthrough that we had, that we published, that we've told OpenAI about, and that we've been basically developing into the product line in the background, Atari is a signal to the machine learning community and those in the deep learning space who, by the way, they were the ones no one believed in, early 2000s till they had a breakthrough paper in ImageNet that led to this. The paper we're planning on putting out this summer, showcasing the breakthroughs we're about to walk you through, giving you a preview of, is demonstrating exactly that. The better, cheaper, faster approach, because we've been able to break through what's called the Bayesian wall, the ability to show that actually you can model information in a superior way that's more accurate, that is transparent, that is far more efficient, and as a result, much cheaper. Let's keep going.
So I think we've made everybody wait long enough. Let's get into this. Can we do that? Let's talk about MNIST briefly.
Let's skip MNIST.
Okay.
So we've come up with not the Atari 100K challenge. If the goal is to do human-like learning and performance, we want to beat everyone else, not at a 100K, which is 2 hours of gameplay, but we want to show that that can be done in 12 minutes. So this is the equivalent of, the Cybertruck beating a Porsche off the line while carrying a Porsche, which some of us all saw, right?
Yeah.
So,
yeah, go ahead.
So this uses continual learning. The other AIs cannot do continual learning. They
What's
often
no
even
replay
cheat
mean?
with this sort of replay thing. They actually get to replay over and over again. We're just gonna go right through. Sample efficient will be 1,000% more sample efficient. Explainable predictions. The others cannot explain what they're doing. They're just a black box. We'll show you exactly what we mean by explainable, and do it on standard hardware, like a laptop, not a GPU cluster from NVIDIA. So in every single mark, we're going to demonstrate how we can basically beat every other major algorithm, including the top ones, in a fraction of the time.
So
a fraction of the cost.
So we're about to go and see the first kind of view of this. What we're going to see is we are the green. The versus system is the green paddle in this, and we're going to show Pong. And let's talk through that.
Well, let me first explain why Pong is relevant.
Okay.
So in papers we've already presented, based on Carl Friston's work, we've shown that neurons in a petri dish, we could teach to play Pong using active inference mathematics. That means biological neurons in a petri dish learning to play the video game Pong, bridging the biological and software gap. Using that exact same mathematics, but without physical neurons, we're able to do that now in software by itself, because the science applies from the biological system to now the digital system. What you're seeing on the left here is our agent we call Optimus. And up above, you're seeing the total number of steps, 500 and something. Now remember, the total number of steps in these other systems, they get 100,000 steps or frames. DQN is that very first one to basically beat human level performance at Atari 100K. At 10,000 steps, it's just that little green one is just kind of wobbling around at the bottom. It doesn't know what to do. Efficient zero is Alpha Zero, which is the one that beat Lisa Doll at Go, trained up to become hyper efficient at Atari 100,000K. At 10,000 steps, it's just wiggling around. What is this proving? That our agent, if you look at it on the left here in green, is able to predict where the ball is going to be and put itself into position. It's doing human-like play. Now, on the far left, what you're seeing is a bunch of these little sort of trajectories that are showing where it thinks the physics of the ball is going to go. And then you'll see those little sort of red rectangles behind it. It's trying to predict where it needs to be in space. So I need to kind of line myself up with this position. I think the trajectory is going to go here. And those elliptical circles it has a greater degree of confidence in the middle, but it might might be that the thing goes into, like I say, the lighter green areas. So you're seeing explainability because we're looking into the brain of the agent. This is not even possible with any deep learning model at all today. This is why when they come out and they say, show the founding fathers with Gemini, and it turns out that they generate them because they overtuned the thing to be, let's say, diversity sensitivity. It makes them all Black and Native American. And they can't go in and fix it immediately because they have no idea really where it is in that giant mix. So explainability is critical to the evolution of these systems, especially not just generating funny pictures or trying to be historically accurate or not, which is important, but in real world automation, where you want to know why the car made that decision to stop, go left, forward, straight, or whatever. So what you're seeing right here is us beating the state-of-the-art models that have had 10 years of research and $1 billion in human level play in 12 minutes. Now, the details of this are going to be published in the paper in the summer, and the level of rigor we have to do has to meet the academic standards that apply to the conferences that you submit these to, that then you're trying to basically win the top paper, which we actually expect to do here. But what you're seeing is a snapshot of something no one sees, because no one ever gets to look at the underlying research that Google or Apple or Meta or Microsoft are doing. The public doesn't get to see the progress here. They don't get to invest in those companies by looking at their advanced research before papers are published. You're getting an early snapshot because we're confident that this has broken the Bayesian wall. This is hyper efficient. Let's keep going, James, and show some of the other aspects of this that make it better, cheaper, faster. So if you just go ahead, hit play, but then forward till about 70% of the video here.
Mm-hmm. Be close.
You're about 3,000. Yeah, you're about 3,000 steps here, and you're seeing our green guy, right, routinely get into position to return the ball, properly project, and in some cases will even begin to score. The others can't even get out the gate, right? So by about 5,000 steps, we're going to start. We'll start not just returning the ball, but it'll start to score. If you skip ahead just a touch.
Yep. And just so we're clear on this, somebody asked about Optimus. Optimus is the name of our internal name for our engine.
That's right. It's a code name. It's the breakthrough for ChatGPT and all these other systems is called the transformer architecture, and the transformer architecture. The ultimate transformer is Optimus. So that's what we started to call Optimus. Actually, I think this is only the gameplay example, but let's go to the next slide.
Mm-hmm.
So what you're seeing is real-time predictions. It's learning and getting smarter as it's going. And it's able to start doing human-like learning and human-like play. Now, how big is this model compared to the others? Meaning, what's the size? So efficient zero is 10 million parameters. I want you to think of that in terms of like, just let's say gigabytes, right? Optimus is 80,000. That means the total size of the model is a fraction of a fraction, right? It's less than 1% of the size. What does that mean? It means it learns with less data. It means it learns faster because it doesn't have to go through all that data. It also means that the models that we're going to be able to make and that people will be able to build and deploy on Genius can run on small devices, laptops, robots, drones, cameras, watches, where the intelligence can be at the edge on those small devices, learning in real time. Complete paradigm shift from the multi-million parameter sized models. So you've got gigabytes to megabytes, right? In terms of size.
So
doing far more with less.
So people asked sort of what that hardware comparison is, and this is appropriate, I think, for the $7 trillion investment request for hardware. This is what we're doing. Yeah. So conventional approach is you need multiple A100s. Those are the big NVIDIA rigs, GPUs, right? We did this on a laptop. Right? It took hours of gameplay for them to basically get to performance. It took us minutes. They have to basically buffer, restore what they learned, and then train back on it. We just learn continuously the whole time. If we're right,
In about 9 months, you need to start shorting NVIDIA because we don't need that infrastructure. You don't need data centers are not the way to go. This is the IBM mainframe moment versus the Intel moment, right? We're going down the Intel path versus is going to be Intel inside, not a giant mainframe that gets sold to the highest bidder that people, basic access time onto. And this means that you're going to be able to have your own agent operate on your own data on your own computer.
And let's go back and look at the size of this market again.
So, these numbers just get tossed around every quarter. Some group comes out. It's the biggest software market in history. It's either going to be based on deep learning, which has had a 12-year run, which most of you think we're seeing the beginning of, but those of us that have in it are saying, no, you're seeing the end of it. You're seeing the peak of it, right? And go look at all the latest research papers that are coming out. Scale is not all you need. There is no emergence in these systems. They're not going to just magically get smarter. And if you just keep throwing more compute and more data at them, maybe you're going to get incremental gains. I'll give you my greatest example of this. Why did Google, after 1 year, a whole year, who invented all of the underlying technology, who had most of the deep learning engineers in the entire Silicon Valley, with 30,000 people as opposed to 700 people, whatever the number is at OpenAI, came up with Gemini, which is arguably some single-digit percentage by their own benchmarks, better in some cases some of the time, but not really. Why? Because they trained on the exact same data set, and because they're using the exact same types of algorithms, and there wasn't a massive 2-step, 3-step, 4-step, 5-step, 20-step difference. But you just saw one of those. We just showed you with like 99% less data, right? 10 times less samples. We can basically do similar efficiency with 1% of the size of the model. That is orders of magnitude. That is not 1%, 2%, 3% better, right?
Perfect.
That's 1,000% better. Let's keep going. So what are we really talking about here? You're placing a bet, right? Now, I'm not telling you to short NVIDIA right now, and this is not investment advice. But if you're invested in Versus, here's what you're betting on, that there's two hills. And the artificial hill, they're reaching the peak at. And the more you look, the more you're going to see this. Don't believe me? Go follow Gary Marcus on Twitter. Every hour, he's going to tell you something that's not working in these systems and why nothing's changed in 10 years. Because they can't reason, they can't plan, they can't learn in real time, and they can't basically adapt and can't share information with each other. We don't think that this is the hill towards AGI, ASI, or anything else. We think they're at the peak of that hill. And if you don't, and you can find ways of investing in those companies, I wish you the best of luck. But we're rather confident that even though we're a little lower on our hill is a much bigger hill, and we're the only ones leading the charge. And that this is the one that actually leads to the type of real world, scalable, multi-trillion-dollar automation markets that everybody wants. Not systems that are giant black boxes that cost, the power of a small sun to basically operate. And that better, cheaper, faster approach is going to win. And we do believe that over the course of the next couple of years, we're going to emerge as the market leader with evidence of this on a quarterly basis, as outlined in the research, which we'll highlight in just a minute. So what do we mean by better? There's these benchmarks that we're showing you were just a snapshot of our early tests. This is not the final. Pong is not the thing. We're going to plan on doing all the games, and we'll share more results along the way as we go here. And in the summer, we'll plan on publishing these papers, and everyone can see them, and the whole world can come at us and try to critique them. But our goal is to beat every single AI model at 10K with superhuman level performance in 12 minutes, right? We're also going to go after them at the 100K and show what we can do at the 100K level. But even though we plan on beating all of them at their own game and with 10 times less compute power and information and data, it doesn't even matter. Why? Because none of us care about video games, and benchmarks and little fixed worlds, as interesting as that is not really what the market is about. The market is about one key thing. How do we get the power of intelligent software to go automate things intelligently in ways that can't harm us, right? But create better efficiencies by having a type of model that doesn't just learn from scratch, because that's what we're showing you. We're showing you learning from scratch, right? But there's a little trick here that active inference has that none of the other models have, which I'll just conclude with today. They can learn, and then they can share what they learn with another agent that then can learn something else. Those two agents can learn two new things and then share that with a third agent that now learns everything. That wisdom that we have, that sort of what we learned from the ancestors that came before us, that continuous learning capability is something completely novel to active inference. But not just a single agent learning, the ability to have shared intelligence, meaning that the knowledge that one agent has can be shared with another agent. Copy pasting intelligence, skills, capabilities, details of those into a new agent that can learn something new and add on to that. So copy, paste, adapt, copy, paste, improve, improved continuous learning that's shareable across many, many different agents. And what were we doing? We're building a platform that lets everyone develop their own agents. You want to build a better camera for Ring, that they want to build a better camera, a better agent that learns your face when you walk up. They can't do that because they don't have your face in the training data. But now they could with VERSes. How about autonomous vehicles that learn how to adapt to the environments that they're driving in, right? What about new types of recommendation systems that fine-tune themselves to you, and then personal agents and all the rest of that. So better is based on this fundamental breakthrough of being able to model data, multidimensional data and probabilistic data, which is richer data, which provides for a level of confidence and explainability in ways that are also simply better. So better, cheaper, faster is the game. The point of the benchmarks is to announce that to the machine learning world, of which we've already shared this with some of the top folks in some of the big tech industries and gotten the most amazing responses that this is completely groundbreaking, a completely novel approach, and completely could upseat deep learning. And yet I'm pointing out to you that those benchmarks actually mostly matter in that academic environment, which is a very important place for validity. But what's really interesting is that the capabilities we're putting into Genius now that we'll begin to launch in the summer is going to start to enable these so that people can start to develop those, and the till starts to run on basically revenue that then scales up. So here's that sort of snapshot. We've got some benchmarks we're going to be showing around image recognition that are coming out in the spring, the Atari 10K and 100K in the summer, and then the Melting Pot Challenge, which is a multi-agent challenge that Google and others try to do, which no one's been able to win. We intend on beating everyone else at that. We're going to, over on a quarter-by-quarter basis, take out every one of the deep learning pillars. By the end of the year, we believe we will have completely turned over the entire deep learning foundation. And even the industry itself will have to admit that this is a better, cheaper, faster approach. Down below, we're going to be rolling out the Genius beta. So we're in tests with some big customers now. We'll be announcing some of those as it starts to roll out at the end of spring in June. And then that will be a continuous beta that will increase, get larger and larger in size as we start to merge these Optimus capabilities into Genius over the course of the year. And then come out of beta next year, having beat everyone in the industry at their own games, now with all these capabilities to do things that none of them can even do. And 2025 is teed up with the full version of V1 of the Genius product ready to go. And that's pretty much the plan.
That's amazing. We are at the top of the hour. Well done, Gabriel, on coming in almost exactly on an hour. One question I did want to address is what is happening with the beta on the Genius side. So we are continuing. We actually had more interest than we could handle. I think we're over 2,000 or more beta customers that have signed up. So there are more and more coming in. And that work is going really well. So just wanted you to be aware that because we stopped doing press releases and things about that, it was actually we were overwhelmed with the amount of interest in using Genius. So that's going really, really well. A couple of housekeeping items to close this out. This will be posted later on today, and wherever possible, we will go back and address these questions and things that are in the chat. Really appreciate everyone watching and staying the full time. And we're looking forward to showing you more of the work that we're doing here because it's exciting to us internally, and it's really encouraging and exciting to be able to share it out with our investors and our fans and everybody who's taken the time to watch today. So thank you very much, and we're looking forward to seeing you all soon.
Thank you, James. Thanks everyone for joining. Look forward to the next round.